Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Tonight, you are drifting into a story woven from darkness, from gravity, and from the quiet beginnings of everything we know. A story that unfolds gently, slowly, as if the universe itself were exhaling. You are here to rest, to let your thoughts loosen, to let curiosity glow softly like a distant star seen through fog. And you are here to listen to the earliest memories the cosmos ever carried. Because long before galaxies spun, long before planets formed, long before light itself filled space, the universe held seeds of something deeper, something mysterious, something that would one day anchor entire galaxies, black holes. But not the violent ones we imagine today, not the monstrous engines tearing stars apart, or the brilliant quasars shining brighter than galaxies. No, the ones we will explore tonight are quieter, older, delicately woven into the earliest fabric of reality. They are the first black holes. The universe's ancient fossils, silent witnesses to a time before time felt familiar. So let yourself drift, gently, as we move backward through cosmic history, not in a fast or abrupt leap, but like sinking into warm water, descending layer by layer, through memory, through silence, into the soft dark that once filled everything. Imagine the universe not as a distant and unreachable place, but as a vast, calm ocean, slowing, cooling, stretching out in all directions. A place where gravity whispers, where light has not yet been born, and where the first black holes are only possibilities, shadows waiting to take shape. In this quiet descent, there is no hurry, no pressure, only a gentle unfolding of ideas, one after another, like ripples spreading through still water. You might sense your breathing slowing, your shoulders lowering, your thoughts becoming softer, lighter, as if they, too, were floating through the early cosmos. Because the beginning of this story is not harsh, not explosive, but deeply calm. Before the first stars burned, before the first atoms fused, the universe was cool and dark, a soft expanding fog of hydrogen and helium, stretching into a silence so deep that even light had nowhere to go. In this darkness, the earliest seeds of black holes were gathering quietly, waiting for gravity to weave them together. But tonight, we're not racing toward them. We're drifting, like dust in an ancient beam of unseen light, letting the story unfold in its own natural rhythm. As you settle deeper into this narration, feel the softness of this journey. Feel how the mind relaxes when the universe slows down. Feel how the darkness becomes gentle, welcoming, not empty, but full of potential. Because darkness in the early universe was fertile, it held everything that would come, every star, every galaxy, every world, and every black hole, all of it waiting, quietly, patiently, for gravity to gather the first threads of structure. Let yourself imagine that darkness, not as a void, but as a cradle, a deep cosmic stillness from which everything would rise. And in this cradle, black holes were not monsters, but infants, small, fragile seeds of immense future power. They were memories in the making, waiting for matter to fall inward, waiting for the first stars to collapse into them, waiting for their place in the universe's earliest architecture. As you relax further, imagine yourself drifting through billions of light years of space, not moving quickly, but gliding smoothly, as if carried by a soft current. Around you, nothing but darkness, a pure, quiet black, the universe before illumination, before structure, before time felt like time. This is where our journey begins, in gentle prelude, with no need to rush. Because the story of the first black holes is also a story about calmness, about slow formation, about the universe taking its time to understand itself. Black holes are often described with drama, with violence, with cosmic destruction. But their earliest history was serene. It unfolded over millions of years, in silence, with matter drifting together, clumping gently, falling inward with the patience of the cosmos itself. The introduction you are hearing now is not meant to explain everything at once, but to bring you into the right state of mind. A state of open curiosity, soft awareness, and peaceful surrender to sleep. Because as you drift off, your mind can hold these ideas like delicate constellations, scientific, yet soothing, analytical, yet gentle, real, yet dreamlike, forming a lullaby built from space-time. Take another slow breath and let your awareness expand, just a little, as if your thoughts were drifting outward into the vast dark sea of the early universe. This darkness is not frightening, not cold, not lonely. It is calm, it is patient. It is the universe before anything complicated existed. The universe before stars, before galaxies, before black holes began to grow and reshape everything around them. Tonight, you are hovering in that ancient quiet. And as you rest in this gentle space, we begin to see the faint outlines of what this story will explore. We will travel through the cosmic dark ages, where the universe cooled into a soft fog of hydrogen. We will watch the first stars ignite, massive, brilliant, unstable, burning through their short lives before collapsing into the first stellar black holes. We will witness colossal clouds of gas collapsing directly into black hole giants. Skipping the step of star formation entirely, we will drift through early galaxies forming around tiny gravitational seeds, watching black holes feed, merge, and grow. We will see quasars blaze across the young universe, their light traveling for billions of years to reach us now. And we will contemplate the possibility that some black holes might be even older, born not from stars, but from quantum fluctuations in the first instance of reality. But all of that will come later. For now, we linger in the softness of the introduction, in the quiet, slow breath of the universe before form, in the gentle gravity of beginnings. Let yourself settle into this feeling, this sense of drifting through ancient space, with no goal but calm exploration. Black holes, in their earliest history, were not tearing space apart. They were forming, shaping, resting in darkness, quiet as a sleeping universe. And as you listen, your mind can mirror that calm, the rhythm slow, the ideas spacious, the imagery vast but gentle. This is not a race through cosmic history. It is a soft glide through the most tranquil chapters ever written in the universe's story. And you floating through this calm are part of that story now. We move at the pace of gravity itself. Slow, inevitable, patient, letting the darkness cradle us as the earliest black hole seeds begin to shimmer in the distant future. For now, though, the universe remains quiet, dim, unformed, a perfect place to rest, a perfect beginning for sleep, a perfect descent into the first section of our journey, before light. Before light, the universe was a place without form, a vast, cooling ocean of invisible matter stretching outward in all directions, quiet, calm, almost perfectly smooth. To imagine this era, you must let go of the idea of stars, of galaxies, of glowing structures. None of those existed yet. The universe in these early epochs was filled only with a diffuse haze of hydrogen and helium, a soft, cooling fog left over from the universe's earliest expansion. It was neither bright nor dark in the way we think of those words. Light had nowhere to scatter, nowhere to reflect, nothing to illuminate. It was a darkness that did not hide anything. A darkness that simply was. A peaceful, pervasive quiet that filled everything. This is what the universe was like before the first stars. Imagine yourself drifting through that vastness, moving slowly through clouds of hydrogen so thin you could travel 1,000,000 kilometers and never feel a single atom collide with you. The density was unimaginably low, yet it was all the universe had. A smooth, gentle fog stretching across billions of light years, cooling with each passing moment, settling into a tranquil equilibrium. And yet, within that stillness, tiny imperfections existed. Not visible, not dramatic, but small regions where the density was ever so slightly higher than in the space around them. These tiny differences, 1 part in 100,000, were enough to shape the future. Gravity, soft and steady, began to gather matter toward those denser spots, slowly, patiently, as if sculpting the earliest structures from the faintest hints of form. This gathering was delicate. Nothing clumped quickly. There were no sudden collapses, no bright flashes, just smooth, gradual motion over millions of years, matter drifting inward, responding to gravity's quiet pull. Even in perfect darkness, the universe was moving. It was preparing, The plasma of earlier times had cooled enough that electrons settled into atoms, creating a transparent cosmos for the first time. Before this change, light had been trapped, scattered endlessly by free electrons in the hot early universe. But now, with electrons bound to nuclei, photons could finally travel freely, and yet they illuminated nothing. There were no stars to ignite, no planets to reflect their light, no galaxies to gather them, only hydrogen fog, cooling, expanding, sinking deeper into the cosmic night. The plasma was gone, the universe was finally transparent, and yet it remained invisible. You float there, in this gentle emptiness, surrounded by silence so complete that even the idea of sound feels too loud to imagine. This was not a void. It was fullness, a universe brimming with matter in its simplest state, waiting for gravity to weave it into something more. And gravity, soft as a whisper, had already begun its work. The denser regions, small, delicate pockets of matter, started to draw in the surrounding gas slowly and perceptibly over immense stretches of time. These regions were the first halos, the first gravitational wells, the earliest structures in a universe still devoid of light. They were not yet stars, not yet galaxies, not yet anything we would recognize today, but they were foundations, seeds of form, gathering mass for a future they could not yet reveal. And within these forming halos, dark matter played the leading role. Invisible, non-interacting, yet massive, dark matter made up most of the gravitational pull in these early structures. It shaped the universe long before light did. Halo by halo, clump by clump, dark matter sculpted the scaffolding on which the luminous universe would eventually be built. Without dark matter, there would have been no place for gas to gather, no gravitational wells to cradle the first stars, no framework for galaxies to form. And yet, in this section, we remain before any of that happens. We stay in the dark ages, in the slow dance between hydrogen fog and dark matter halos, watching the universe's earliest structures take shape in silence. In this era, darkness was not empty, it was full of potential. Every point of gas held the possibility of collapsing into something new. Every gravitational well held the blueprint of future galaxies. It was a time of quiet preparation, a time when the universe was arranging itself for the first great transformation, the birth of light. But light had not yet arrived. What fills this section is the calm before ignition, and in that calm, the conditions that would make the first black holes possible were slowly coming together. For black holes are born from collapse, and collapse cannot happen without gravity pulling matter inward. The darkness of this era allowed matter to cool, to gather, to settle into dense pockets that would one day ignite as stars and later collapse into black holes. The quiet conditions of the cosmic dark ages were essential. No radiation pushed against gravity, no starlight heated the gas, no powerful winds from massive stars disturbed the forming structures. Everything was slow, gentle, balanced. This is the environment in which the first black holes would someday arise. Not yet, but soon. For now, we drift through this softness, this delicate prelude, this era where gravity was writing the opening lines of the universe's first structures. Hydrogen fog, dark matter halos, cooling, contracting, preparing, all of it necessary for the first stars to ignite and the first black holes to form from their depths. The cosmic dark ages were a cradle of potential, a vast, silent womb from which the luminous universe would one day emerge. After a long era of darkness, after the universe cooled, drifted, and settled into quiet halos of hydrogen and helium, a profound transformation began to unfold. The first stars were preparing to form, not suddenly, not explosively, but through an ancient, patient gathering of the simplest elements in existence. Hydrogen and helium, these two gases, the universe's first ingredients, held within them the potential for light, for heat, for fusion, for the cosmic dawn. And yet for millions of years they drifted quietly in near-perfect darkness, until gravity, soft and persistent, pulled them inward. Slowly, inevitably, as if the universe were inhaling. Imagine a vast cloud of hydrogen, cold, weightless, filling space like a thin mist. Now picture gravity subtly gathering that mist inward, tightening it, allowing regions to grow denser, warmer, heavier. You might imagine the gas glowing as it compresses, but in reality, even this stage was shrouded in darkness. The forming star was still hidden, still cool, still waiting for its core to reach the temperatures needed to ignite fusion. This process was slow, as if the universe were reluctant to let the first light appear. But slowly, steadily, the cores of these collapsing clouds became hotter. The pressure increased, the atoms collided more violently, the center grew dense enough to trap its own heat, and something remarkable began. Hydrogen atoms, simple, ancient, abundant, started to fuse. They merged into helium, releasing energy, light, heat. A star was born. And not just any star. These were the population 3 stars, the very first generation of stars the universe ever produced. They were unlike anything that exists today, because they were made only of hydrogen and helium, with no heavier elements, no metals. Their behavior was extreme. Without elements like carbon or oxygen to help cool the star's gas, the collapsing cloud could not fragment into smaller stars. Instead, the gas gathered into enormous masses. Stars hundreds of times the mass of the sun, maybe even 1,000 times. Colossal spheres of blazing plasma with lifetimes measured not in billions of years like the stars of today, but in only a few million. These stars were hot beyond anything we see now. Their cores reached temperatures so extreme that fusion ran wild, burning through hydrogen with furious intensity. Imagine a star so bright that its light would have made entire regions of the early universe glow, and yet no one was there to see it. No planets, no observers, no galaxies as we know them. Only darkness and this sudden blazing flame of the universe's first starlight. The energy pouring from these stars was immense. Their radiation blasted hydrogen apart, ionizing the surrounding gas, changing the chemistry of the universe forever. They were beacons that pierced the cosmic dark ages. They were architects of the universe's first transformation. Yet even in their brilliance, they carried fragility. Because their size, their mass, their metal-free composition made them dangerously unstable. Their cores fused elements rapidly, building heavier nuclei under crushing pressure, until one day the balance collapsed. In stars perhaps 100 to 300 times the mass of the sun, the final moments came in violent flashes. Their cores reached temperatures where photons became so energetic they broke apart atomic nuclei, a process called photodisintegration. This robbed the star of pressure, triggering a catastrophic collapse. In an instant, gravity overwhelmed everything. The outer layers imploded, then blasted outward in titanic explosions, supernovae brighter than entire galaxies. And at the very center, the core collapsed into darkness. A black hole, one of the first the universe had ever seen, a seed. Small compared to the giants of later epochs, but powerful enough to shape everything around it. These early black holes were born from stars that burned briefly and died violently. Other population 3 stars, the extremely massive ones, may have skipped the explosion entirely, collapsing inward directly, their entire mass falling into a point of infinite density, forming black holes thousands of times the mass of the sun. And all this brilliant burning, all this collapse and rebirth happened in a universe still young, still dark, still forming its first structures. These stars were the first engines of chemical evolution. They produced the first heavy elements, tiny amounts of carbon, oxygen, nitrogen, and iron, which would later seed the next generations of stars. They lit the universe for the first time, and when they died, they left behind the earliest black holes. These black holes were small compared to the supermassive ones we find at the centers of galaxies today. But they were the seeds from which much larger structures would eventually grow. We will explore that growth in later sections. But for now, we remain with these stars at their birth, their burning, their collapse. We linger in the glow of the universe's first light and in the shadows of the black holes that followed. Inside the earliest stars, the temperatures were unlike anything the universe had known before. Not millions of degrees, but tens of millions, even hundreds of millions, in the deepest parts of their cores. Heat so intense that atoms had no identity, only nuclei colliding in a dense, furious plasma. Imagine a place where matter is stripped down to the barest possible form, where protons and electrons no longer live as partners, where every particle is part of a violent, swirling dance of heat and pressure. This is what the first stellar cores were like. These primordial stars were so massive that gravity pressed their interiors toward crushing densities, creating conditions so extreme that hydrogen fused at a rate far beyond anything in the modern universe. Fusion, in these stars, was not gentle. It was not slow or balanced. It was explosive in nature, held in check only by the star's enormous weight. Hydrogen nuclei slammed together with such force that they merged into helium, releasing torrents of energy in the form of gamma-ray photons. These photons struggled to escape, caught in a maze of scattering, absorbed, re-emitted, redirected millions of times before they finally reached the star's surface, and then wandered into the darkness of the early universe, becoming the first meaningful light the cosmos had ever seen. The temperature at the core of these primordial giants was so high that fusion processes we barely see today became dominant. Not just the proton-proton chain, but the more powerful CNO cycle, even though almost no carbon, nitrogen, or oxygen existed. Yet with the tiniest trace amounts created from quantum fluctuations or formed in the first moments of a star's life, the CNO cycle began to run with extraordinary intensity. Every tiny seed nucleus, every carbon atom, acted as a catalyst for fusion reactions that burned hydrogen at terrifying speed. These stars lived right on the edge of instability. Their cores were so hot, their fusions so intense, that small changes in temperature could create enormous shifts in the star's luminosity. They pulsed, breathed, expanded and contracted in slow, massive rhythms, like titanic hearts beating in the quiet of the early universe. Because they were metal-free, their surfaces offered little resistance to the energy pouring upward from their cores. Light escaped freely, radiation streamed outward, and the star shone with a brilliance we can scarcely imagine. These were the first beacons, the first cosmic lighthouses, the first sources of illumination in a universe that had never known light. And yet, for all their brilliance, they were fragile. Their very size made them unstable. Their cores burned through hydrogen so rapidly that their lifetimes were shockingly short, a few million years, fleeting moments on the cosmic timescale, and then the fuel ran out. When the hydrogen in a star's core was exhausted, gravity tightened its grip. The core contracted, heated, and began to fuse helium into heavier elements. Carbon, oxygen, neon, magnesium, elements that did not exist before the lives of these stars. With each new fusion stage, the star grew hotter, more unstable, until iron began to form at the very center. Iron, the element that ends a massive star's life. Because fusing iron does not release energy, it consumes it. And when iron accumulates, the delicate dance between gravity and radiation breaks. The outward pressure of fusion weakens. Gravity wins. In an instant, the core collapses. The star's interior plummets inward, falling in free fall, densities rising to extremes no other environment can reach, temperatures surging beyond comprehension, matter smashing together in ways we cannot fully imagine. If the star is massive enough, the collapse becomes unstoppable. No force in the universe can withstand it. Not electron pressure, not neutron pressure, not any form of degeneracy. The core shrinks past every barrier, past every limit, until space-time itself curves inward, and a black hole forms. The earliest black holes were born in this way, in the violent endings of the first stars, but also in the peaceful inevitability of gravity pulling matter inward until no outward force remained to resist it. Yet black holes did not always emerge from explosions. Some primordial stars were so massive, so enormous, that when their cores collapsed, the entire star fell inward. No supernova, no outward blast, no brilliant finale, just a silent implosion where mass slipped past the point of no return. A direct collapse into darkness. These collapses created black holes with hundreds or even thousands of solar masses, giants compared to the typical stellar mass black holes we see today. Each collapse was a transformation, matter becoming gravity, energy becoming curvature, star becoming singularity. The universe was learning how to make black holes, learning how to store energy in pure gravitational form, learning how to create the engines that would one day sit at the centers of galaxies and reshape the cosmos on scales far beyond the first stars. The earliest black holes were the universe's first gravitational archives, tiny seeds in an endless dark ocean, anchors that would one day pull galaxies into being. Their creation marked a turning point, a moment when the cosmos began to build complexity from simplicity, structure from collapse, light from darkness, and darkness from light. When the first stars reached the end of their brief and brilliant lives, the universe experienced collapse on a scale it had never seen before. These ancient giants, made only of hydrogen and helium, burned through their fuel so quickly that the balance between radiation and gravity was fragile from the very beginning. And when that balance finally failed, their deaths unfolded in a way that shaped the entire future of the cosmos. Inside these massive stars, iron began to accumulate, the final terminal element that ends fusion rather than powering it. As iron formed, the outward pressure of nuclear reactions weakened, and gravity, which had been patiently waiting through the star's entire lifetime, tightened its grasp. The core collapsed in a fraction of a second. Temperatures climbed to billions of degrees. Densities soared far beyond those found in any ordinary matter, and the star's center imploded. Some stars ended in spectacular supernova, their outer layers ripped apart, sending shockwaves through the surrounding gas, seeding the cosmos with the first heavy elements. But many of the earliest giants collapsed with too much mass for an explosive revival. Their gravity was overwhelming, their cores fell inward without resistance. No blast, no eruption. A quiet, unstoppable implosion into pure darkness. When the collapse reached the point where no known force could support the matter within, a boundary formed, an event horizon, and beneath it, a singularity, a black hole. And so the universe created some of its first gravitational seeds. They began small compared to the titanic structures of later times, but in the early cosmos, small did not mean insignificant. These black holes often started with masses of tens, or perhaps hundreds of suns. Compact points of extreme curvature, born from the deaths of the first massive stars. Inside them, the entire life of a star was folded into gravitational memory. Outside them, their influence began to stretch into the silent hydrogen fog. Even a tiny black hole exerts a gravitational pull that extends far beyond its event horizon. Matter drifted toward them, very slowly at first, guided by the gentle pull of their intense curvature. But the early universe was not an empty place. It was threaded with filaments of dark matter, cosmic scaffolding that shaped the large-scale structure of everything to come. These newborn black holes found themselves embedded inside those filaments, inside halos made mostly of invisible, collisionless matter, and the halos responded to their presence. The gravity of a tiny black hole is dwarfed by the mass of a dark matter halo. But the halo's structure helped funnel gas toward the black hole. Slow streams of hydrogen moved inward, cooling, settling, drifting into the center of the halo. There, the black hole waited, patient, silent, hunger wrapped in space-time. Gas approached gently, orbiting, spiraling inward over millions of years. The black hole fed slowly but steadily, and each particle of hydrogen that crossed the event horizon was erased from the visible universe, converted into deeper curvature, deeper gravity, a slightly larger singularity. These seeds, though tiny, were essential. Without them, the early halos would have remained diffuse, their gas lacking a central anchor. Black holes provided that anchor. They acted as gravitational centers around which matter collected, cooling, condensing, eventually forming some of the earliest proto-galactic structures. In many ways, the first black holes were not destroyers, but organizers. They helped define the architecture of the young cosmos, guiding gas into the dense regions where stars would one day ignite in great numbers, regulating the flow of matter through the earliest forming clouds, shaping the dynamics of the tiny proto-galaxies that flickered into existence hundreds of millions of years later. Their gravity was a quiet sculptor, not loud, not violent, but steady, enduring, subtle. And because these black holes were embedded in dark matter halos, they often migrated toward the densest parts of those halos, falling inward like stones settling at the bottom of a calm pond. At the centers of these early structures, gas began to accumulate more rapidly. Streams of material fed the black holes, sometimes forming small, primitive accretion disks, dim spirals of heated gas glowing faintly in the cosmic night. The heat and light released by this infalling matter were tiny compared to the later brilliance of quasars, yet for the early universe they were meaningful, the first hints that black holes could act as engines of light as well as darkness. Even when not actively feeding, these small black holes played a crucial role. Their gravity stabilized the centers of early structures. They prevented gas from dispersing. They encouraged collapse rather than expansion. Every tiny black hole acted like a seed, a gravitational nucleus that would help shape the galaxy around it. And over time, many of these black holes moved toward each other as their host halos merged, drawn together through the slow evolution of cosmic structure. These mergers were gentle in the early universe. Soft coalescences of mass and memory, two black holes sinking toward each other inside a shared halo, their orbits tightening, their gravitational waves quiet and low frequency, until they united into a single, larger seed. The universe was assembling its first black hole population, little by little, collapse by collapse, merger by merger, weaving gravity together into compact knots that would one day grow into giants. These early seeds were small on the scale of cosmic phenomena, but immense in their importance. Without them, the formation of galaxies would have been slower, more chaotic, less organized. With them, gravity had focus points, centers of curvature that helped structure the universe's earliest architecture. In the young universe, not every path to a black hole required the life and death of a star. There were places, rare places, where the cosmos followed a different script, a quieter, stranger script, where gravity did not wait for ignition, did not wait for fusion, did not wait for a star to blaze and die, but instead gathered matter so smoothly, so symmetrically, that the gas never had the chance to fragment into smaller pieces, never had the chance to collapse into starlight. These were regions where stars never formed at all, where the conditions were so unique that the universe allowed an entirely different kind of collapse, a slow, enormous inhalation of primordial gas, falling inward without interruption, until it reached a point where collapse could no longer be stopped. The early cosmos was laced with halos of dark matter, the invisible scaffolding on which all structure hung. Most halos allowed gas to cool and fragment, forming clusters of bright, massive stars. But a tiny fraction had conditions that prevented cooling just enough. Halos bathed in gentle ultraviolet radiation from neighboring stars, not strong enough to blow the gas apart, but strong enough to suppress the molecules, especially molecular hydrogen, that would normally allow gas to cool. Without cooling, gas cannot break into small clumps, and without clumps, stars cannot form. So the gas remained smooth, and gravity continued its steady pull, drawing millions of solar masses of hydrogen and helium into the center of these rare halos. Imagine a cloud hundreds of thousands of light years across, falling inward in a slow, majestic contraction, a cosmic glacier of hydrogen fog, descending toward its own core over millions of years, its collapse uninterrupted by stellar radiation, supernova winds, or turbulent feedback. A quiet fall, clean, symmetrical, inevitable. As the gas compressed, it heated, but could never cool enough to break into star-forming pieces. Instead, it formed a single colossal structure, something halfway between a star and a galaxy, a gigantic object so massive that its very existence defied the logic of modern astrophysics. We call such objects supermassive protostars, or, more evocatively, quasi-stars. These were titans, hundreds of thousands to millions of times the mass of the Sun, their cores collapsing inward even as their outer envelopes remained swollen and luminous. But despite the light they emitted, despite their energy, their interiors were unstable. In their centers, gravity was too strong, pulling matter inward faster than pressure could push outward. The core collapsed, and a black hole formed inside the star itself. A black hole born not from death, but from uninterrupted accretion. The newborn black hole did not destroy the star immediately. Instead, it fed on the star's interior, growing rapidly while the outer layers remained gravitationally bound, as if the star were swallowing itself from the inside out. This process allowed black holes to grow far larger than any ordinary supernova remnant, producing objects 100,000 or even 1,000,000 times the mass of the Sun in a remarkably short time. These were the direct collapse black holes. No explosion, no shockwave, no scattered debris, just collapse, smooth, complete, relentless, guided by gravity and the inability of gas to cool and fragment. In the early universe, these black holes were rare, but where they formed, they changed everything. Their enormous masses gave them gravitational influence far beyond that of the smaller seeds formed from stellar deaths. They acted as anchors for the earliest massive galaxies, drawing gas inward, creating swirling disks, funneling matter into structures that could begin star formation on a massive scale, structures that would later host quasars bright enough to be seen across the entire observable universe. Yet the origin of these titans remained gentle. A collapse without violence, a fall without rupture, a quiet descent into infinity. The young cosmos needed these giants. Without them, the universe would not have had enough time to produce the supermassive black holes observed less than 1 billion years after its beginning. Black holes weighing billions of suns, far too large to have grown from ordinary stellar seeds in such a short time. These early titans provided the head start required for cosmic history to unfold as it did. And yet, despite their importance, their births were almost peaceful. A cloud collapsing, a core contracting, a boundary forming, a hole in space-time opening, darkness taking shape, all of it happening in silence so vast that even light felt small within it. The mystery of how such giants appeared so early remains a question that astronomers continue to explore. Yet the physics behind their birth is clear. Prevent fragmentation, maintain smooth infall, allow gravity to act without interference, and a titan will form. A black hole born directly from the collapse of a massive primordial cloud, a gravitational engine capable of shaping an entire galaxy's destiny. In the still-forming universe, there were places where gas flowed like rivers in the dark, where streams of hydrogen and helium slid through the great structure of space-time, like silent currents drifting through an invisible ocean. And within these currents, the black holes of the early cosmos began their long process of growth. Their hunger was not violent at first. It was quiet, a gentle influence felt across great distances. Gas responded not with chaos, but with a slow inward drift, as though gravity were whispering and matter were listening. As the gas approached, its path curved, spiraled, flattened, forming a disc-like structure that warmed with every orbit. This glow was faint compared to the blazing quasars yet to come, but in the darkness of the early universe, it was a remarkable thing. A circle of heated gas, shimmering softly in a cosmos still learning how to shine. This disk, thin, broad, and spinning, became the main way black holes consumed matter. Accretion. The infalling gas lost energy over time, its orbits tightening, its temperature rising, until it reached the inner edge of the disk and crossed a boundary from which no return was possible. Each particle that fell carried mass inward, growing the black hole one atom at a time. The rate of this feeding depended on many things: the density of gas, the temperature of the halo, the strength of radiation pushing outward. But in these early epochs, there were moments when conditions aligned and the inflow became steady, almost like a cosmic tide drifting inward over millions of years. As this feeding continued, the black holes grew, slowly at first, then faster as the surrounding structures became more complex. But accretion was only part of their story. There were other black holes scattered throughout the forming halos, tiny seeds from the first stars, larger seeds from direct collapse, all moving slowly under the influence of gravity. Over time, their orbits decayed, friction with the surrounding gas slowed their motion, and they drifted inward. Two small black holes could approach one another in the quiet dark, their gravitational fields overlapping, their spirals tightening, their motion accelerating, until eventually they coalesced into a single, larger entity. The merger was not explosive in the way we imagine explosions, for little matter was ejected. Instead, the collision emitted ripples, waves in space-time itself, gentle oscillations that expanded outward through the dark universe, carrying with them a record of the merger, but leaving behind a more massive black hole at the center. These mergers were essential in the early cosmos. They allowed the population of tiny seeds to combine, to grow, to become gravitationally significant on larger scales. And all of this happened within a vast cosmic framework, the web-like structure that gave the universe its first form. Imagine an enormous lattice stretching across billions of light years, made not of solid metal or crystal, but of invisible matter woven into filaments. These filaments guided the flow of gas, funneling it toward nodes of high density, the same nodes where halos formed, where stars ignited, and where black holes found a steady supply of matter. Along these filaments, gas moved like water through deep channels. Never turbulent, never explosive, but steady, inevitable, driven by the tug of gravitational potential. The black holes residing within these nodes benefited greatly. They sat at the crossroads of cosmic traffic, where streams of gas converged, providing a continuous supply of material to consume. Over time, the halos that contained black holes began to change. gas cooled and settled into rotating structures, forming the earliest disks, the primitive ancestors of galaxies. Stars formed in these disks, first in small numbers, then in growing clusters, lighting the darkness with the faint glow of new nuclear furnaces. But even as these stars formed, the black holes at the centers continued to influence the flow of matter. Their gravity helped stabilize the densest regions, preventing gas from dispersing, encouraging continued collapse, making it easier for new stars to appear. In some places, the black holes heated the gas, their radiation pushing outward, their energy slowing the rate of star formation. In other places, the gas flowed inward so quickly that the black holes entered phases of rapid growth, their accretion disks lighting up like small beacons in the vast night. Over millions of years, these processes, accretion from disks, mergers of seeds, inflows guided by cosmic filaments, and the gradual formation of galaxy-like structures, worked together to shape the first significant black holes. Some remained small, tiny embers resting quietly in the halos that birthed them. Others grew steadily, their mass increasing by factors of 10 or 100, becoming dominant centers around which matter flowed. A few, only a few, became massive enough to trigger luminous transformations, when accretion pushed their output of light to extraordinary levels, revealing their presence in flashes of brilliance that would one day help astronomers measure the shape and distance of the early universe. All of this growth took place in an environment still mostly dark, still cooling, still forming its structure, but no longer quiet. Gravity was now in full conversation with matter, pulling it into patterns, teaching it to collapse, teaching it to orbit, teaching it to shine. The black holes were learning too, learning how to feed, how to merge, how to shape the gas around them, how to settle into the hearts of forming galaxies. Nothing in this era was abrupt. Nothing was sharp. Everything unfolded over long stretches of cosmic time, with gentle interactions, soft collisions, and steady inflows. The earliest black holes grew slowly and quietly, but they grew with purpose, guided by the structure of the cosmic web, supported by streams of gas, and amplified by mergers that combined their gravitational memory. In the quiet dark of the early universe, there came a time when gravity, gas, and deepening structure combined to create something luminous, something powerful, something visible across almost the entire cosmic expanse. Not a star, not a galaxy, but a single, concentrated brilliance rising from the centers of the first massive halos, a quasar. To imagine this phenomenon softly, gently, in a way that lets the mind drift, you can start with the picture of a black hole no longer small, no longer modest, but grown enough to influence its surroundings in far-reaching ways. Think of a black hole weighing millions or tens of millions of suns, sitting at the center of a forming galaxy-like structure. Around it, gas drifts inward. Not slowly now, but in great sweeping currents, dense flows guided along filaments, streams of matter funneling toward the core. As the gas falls inward, it doesn't plunge directly into the black hole. It orbits, it circles, it forms a disk so hot that even hydrogen, the simplest atom in the universe, is torn apart. The disk begins to glow with astonishing intensity, heat rising until the radiation spills outward in all directions, a beacon illuminating the dark. This is the engine of a quasar, a black hole consuming matter so rapidly that the infalling gas heats to incredible temperatures and outshines entire galaxies. To the early universe, this light was extraordinary. Great distances did not soften it. Even across billions of light years, the glow endured, reaching out through space that was still expanding, still cooling, still settling into structure. The brightness of a quasar was unlike anything else, not a gentle star or a cluster of stars, but a point of tremendous radiance powered by gravity itself. As accretion intensified, the disk spun faster, heated further, and emitted radiation across the entire electromagnetic spectrum, from soft infrared to ultraviolet to energetic X-rays that pierced the surrounding gas. This radiation carved cavities in the material around the black hole, pushing gas outward, sculpting winds that flowed into the halo, winds that could reach thousands of kilometers per second. And still the black hole fed. It fed until the inflow and the outflow balanced, creating a rhythm, a luminous heartbeat, that pulsed through the early cosmos. These quasars were rare. They required enormous inflows of gas, massive halos, and black holes large enough to convert gravitational energy into light at extraordinary efficiency. But where they appeared, they became the brightest objects ever produced in the early universe. One of them, known to astronomers today as J342 plus 0928, shone when the universe was only 690 million years old. A child compared to its present age. And yet the black hole at its center weighed hundreds of millions of suns. For such a massive black hole to exist so early, something remarkable had to happen, either extreme accretion or a massive seed born from direct collapse, or both. But beyond the sheer brightness and the staggering power of quasars, there's another layer to their story. Their light became a tool. As it traveled outward, it passed through clouds of gas, regions of hydrogen that still filled much of the cosmos. Some of this hydrogen absorbed specific wavelengths, leaving delicate imprints on the light. Billions of years later, when this ancient glow reached Earth, astronomers captured it, studied it, decoded the patterns. Each absorption line revealed something: the composition of distant gas, its density, its temperature, its motion, its ionization state, and most importantly, its distance in time. Quasar light became a probe, a way to map the young universe, a way to see the end of the cosmic dark ages, the moment when the first stars and galaxies began to ionize the hydrogen fog, a way to trace the growth of structure, the rise of galaxies, the evolution of matter from simple clouds to complex cosmic forms. The earliest quasars were not just bright, they were storytellers. Every photon that left their disks traveled through expanding space, stretching, cooling, reddening, until it carried with it a record of the journey. And yet, despite their brilliance, their appearance was fleeting. Quasar phases do not last long by cosmic standards. They flare, they blaze, they reshape their environment, and then, slowly, they fade as the black hole consumes the nearby gas, as the inflow dwindles, as the disk cools and the radiation subsides. What remains is a massive black hole sitting quietly at the center of a growing galaxy, no longer luminous, but still powerful, still shaping orbits, still influencing the stars around it, still waiting for the next inflow of gas that might awaken it again. In the early universe, these brilliant phases were markers, signposts that told of halos rich in gas, of black holes large enough to ignite accretion disks into blazing engines of light, and of cosmic structures forming rapidly at the crossroads of filaments. The brightness of a quasar was a message that gravity had gathered enough matter to create something extraordinary, that the black hole had reached a threshold where its feeding became luminous beyond compare, and that the universe was entering a phase of rapid transformation. Long before galaxies took their familiar forms, long before clusters and superclusters, long before the cosmic web matured into the structure we see today, quasars lit the darkness, revealing the deep, intricate dance between gravity and light, and showing that the universe was far more active in its earliest ages than we once imagined. Their brilliance was the dawn after the dusk. Their glow was the signal that the cosmos had begun to awaken, to shine, to evolve. And all of this, the brightness, the physics, the distant message carried by ancient photons, unfolds gently, like a soft tide moving across the quiet ocean of the early universe. There is a quieter possibility that lingers at the edges of cosmology, a possibility that reshapes not just the history of black holes, but the entire early unfolding of the universe itself. It suggests that black holes might be older than stars, older than galaxies, older than light, perhaps as old as the first tiny ripples of energy that formed fractions of a second after the universe began expanding. To approach this idea gently, calmly, in a way that lets the mind drift, you have to go to a place before atoms, before cooling, before hydrogen, to a time when the universe was so dense, so hot, so rapidly changing, that space itself was quivering with fluctuations. In that early instant, a moment measured in unimaginably small slices of time, tiny variations in density passed through the expanding fabric of the universe. Most of these fluctuations were mild, barely noticeable, just a little more dense here, a little less dense there, the seeds of future structure. But in some rare places, the fluctuations could have been much larger. If a region became dense enough, even briefly, gravity could overwhelm expansion, compressing the energy into a tiny, compact object, a black hole far smaller than any that formed later from stars. These hypothetical objects are called primordial black holes. They would not be born from collapsing gas or dying stars or even massive halos. Instead, they would have emerged directly from the conditions of the early universe, carved out of fluctuations in space-time itself. A primordial black hole could be as massive as a mountain, or as light as an asteroid, or even smaller than that. Some could be microscopic, so tiny that quantum physics would dominate their behavior. The idea is speculative, but possible. Because in those first fractions of a second, the universe was not calm. Energy surged and shifted. Density rose and fell. Everything was extreme, swift, unpredictable, and gravity was not yet balanced by familiar structures. In this environment, even a slight enhancement of density in a small region could cause the collapse of that region into a black hole. These objects would have been numerous in some scenarios, rare in others, and their masses could span an enormous range. Some primordial black holes would be heavy enough to survive until today. Quiet wanderers drifting through galaxies, pulling lightly on stars, passing through clouds of gas without slowing, hidden because they emit no light, noticed only through their gravity. Others, the smallest ones, would have lived far shorter lives. Because small black holes experience a peculiar effect, they evaporate. This idea comes from quantum physics, the concept that even empty space is not truly empty, that pairs of particles blink in and out of existence, that energy fluctuations occur everywhere, at all scales. Stephen Hawking proposed that near the event horizon of a tiny black hole, these fluctuations could become unbalanced. One particle of a pair falls inward, the other escapes, and as the escaping particle carries energy away, the black hole loses mass. This process, called Hawking radiation, is incredibly slow for large black holes, but for very small ones, especially for primordial black holes with tiny masses, the evaporation could be significant. Some might have vanished long ago, dissipating into gentle radiation, leaving no trace but a faint whisper in the cosmic background. But others, larger ones, could have survived, and these surviving black holes have led scientists to wonder, could primordial black holes be the dark matter? Dark matter, that invisible mass that shapes galaxies, bends light, and forms the scaffolding of the cosmic web, is still mysterious. No particle has been definitively detected, no force has been conclusively identified. So the possibility that ancient black holes, formed from the universe's earliest moments, make up some or all of the dark matter, is both intriguing and deeply speculative. If primordial black holes are heavy enough, they would be stable. They would emit almost no Hawking radiation. They would drift quietly through galaxies, interacting only via gravity. They would be almost impossible to detect directly, but their collective influence could help shape the universe. Observations have placed constraints on how many of these objects could exist. But the idea is not ruled out. It sits in a subtle place, not proven, not disproven, a bridge between known physics and the unknown territory of the early universe. And that is what makes this idea so quietly powerful. It reminds us that the universe's earliest moments may hold secrets far stranger than the structures we see today. It invites the possibility that black holes did not simply arise from stars and gas, but were woven into the universe from the beginning. Tiny relics of a time when space-time itself was unstable, vibrating with quantum fluctuations. These relics, if they exist, would carry the memory of the earliest physics, the physics before atoms, before light, before the cosmos cooled. They would be the oldest black holes, not formed from collapse, but from creation. This idea stands at the delicate boundary between established science and the imaginative frontier, a place where equations meet possibility, where cosmology meets speculation, where the universe keeps some of its oldest secrets just out of reach, whispering them only through gentle hints in radiation, gravity, and the slow evolution of structure. In the great quiet that settles when we look back across the universe's early ages, there is a sense of stillness that feels ancient, patient, as though the cosmos itself is exhaling after a long journey. All the structures we've wandered through, the first stars, the halos of dark matter, the drifting clouds, the glowing disks, the giants born from collapse, and the speculative seeds from the universe's earliest instants, all of them now rest deep within the fabric of the night sky. When we let our mind drift across these eras, across these vast spans of time and space, it becomes clear that the universe remembers everything, not in words, not in stories, but in patterns, in orbits, in the way galaxies spiral, in the way light stretches as it crosses the expanding void, and in the quiet gravity of the black holes that formed long before we arrived. Even now, their influence lingers in ways we can feel but cannot touch. A black hole does not shine on its own, yet its presence shapes the paths of stars, warps space-time, and holds memories of the material it has consumed. These memories are not written in matter, but in gravity, in curvature, in the deep folds of space-time where mass accumulates and time moves differently. When we speak of the universe's first black holes, we are really speaking of the earliest moments when gravity found its voice. Long before the galaxies gathered their spiraling arms, long before clusters and superclusters, long before the web of structure stretched itself across billions of light years, gravity was working with quiet intention. It learned to collapse gas into stars, to shape dark matter into halos, to ignite quasars, to carve filaments, to bring structure to what began as something nearly featureless. And in that learning, black holes became one of its most elegant tools. A black hole is not simply a region of collapse, not merely a point where escape becomes impossible. It is a memory of mass that once existed as gas, as stars, as energy, folded into pure geometry. The earliest black holes were scattered through the young cosmos like silent anchors, holding on to the material that drifts too close, shaping the growth of the galaxies around them. Some grew into giants that shone as quasars, others remained small, quiet embers waiting for the chance to feed again. And still others may have drifted since the beginning, ancient primordial seeds older than atoms, carrying with them a faint, impossible memory of the universe's earliest vibration. When we look out into the night sky, we see only a flicker of what once was. Light needs time to cross the cosmos, to stretch, to shift, to reach our eyes. What we see is always a memory, a record of events that happened long ago. But black holes do not offer us light. They offer gravity, a different kind of remembrance, a different kind of story. Their presence tells us how mass once moved, how gas once flowed, how stars were once born, and how the universe built its earliest structures. In this way, black holes are not destroyers. They are archivists. They hold what the universe has chosen to compress, to condense, to keep. And when we follow the story of these earliest black holes, when we trace their formation from the first stars, from collapsing clouds, from primordial fluctuations, or from the luminous flare of early quasars, we begin to understand that the universe is not chaotic. It is patient. It builds quietly, slowly, with long rhythms and gentle transitions, letting gravity take the lead, letting matter surrender to collapse, and letting light escape into darkness where it can travel forever. In this slow unfolding, every collapse is also a beginning. Every black hole is a threshold, a place where matter enters a new form, and the universe keeps moving forward. When we drift through these ideas with a calm mind and let the imagery settle softly, it becomes clear that we are not separate from this story. Our atoms were forged in stars that formed long after the first black holes. Our world is shaped by the expansion that carried quasars far beyond our reach, and our understanding is illuminated by photons that began traveling billions of years before life emerged on Earth. Yet we are here, thinking about these early ages, imagining the dark, the gas, the collapse, the growth, and feeling in a quiet way that the universe is not distant. It is continuous. It stretches from the earliest fluctuations to the present moment, passing through every stage with a slow, gentle patience. Black holes were there at the beginning, and they are here now. Galaxies were forming in silence, and their shapes still hold the patterns of early gravity. The cosmic web was stretching across space, and we inhabit a small corner of its vast structure. The quasars that lit the dawn have long since dimmed, but their light still moves toward us, still arrives, still tells their story. And the primordial seeds, if they exist, still drift in the dark, silent, ancient, unseen. The night sky that we look up into is not simply a view, it is a memory, a living memory, stretching across time, filled with the traces of stars that lived and died, and black holes that watched quietly from the centers of forming galaxies. When you close your eyes, you can imagine this vastness without needing to understand every detail. You can feel the calm rhythm of cosmic time, the slow shaping of matter and gravity, the patience with which the universe reveals itself. And as the mind grows quiet, as sleep begins to form around you, these ancient structures, these early black holes, and the luminous trails left by quasars settle into a gentle understanding that the universe is vast but not hurried, mysterious but not chaotic, deep but also calming. A place where everything flows from one stage to the next, where every collapse creates new structure, and where every moment is connected to the next moment by the soft gravity of time. You are part of this long unfolding, woven into the same cosmos that shaped the first stars, the first galaxies, and the earliest black holes. And as you drift gently into rest, the universe keeps its quiet pace, soft, ancient, patient, carrying its memories within the silent curvature of space and holding them for all who dream under its endless sky.